specifically at molecular targets. So there are drug targets mostly fall into these four categories here: receptors, enzymes, ion channels, and transporter molecules. Now, I put an asterisk here next to receptors because the way receptor is used in pharmacology is a little bit different than the way it's used in other biomedical sciences, especially immunology. For our purposes here, a receptor is a target protein that is intended to respond to endogenous chemical signaling, endogenous chemicals. So that's all we're only going to call that type of protein a receptor. The rest are better called drug targets, such as enzymes, ion channels, and transporter molecules. So now let's break down into what happens at drug targets or receptors. Now there's agonism, antagonism. These two are the most important things to understand. Antagonism has a preference for the neutral state of a receptor or target. So equals neutral state. In pharmacological terms, we would say it has an efficacy of 0. Efficacy in pharmacology, when it comes to drug targets, actually means how much of an effect that drug has on that target, rather than if it works in a more general sense, like fluoxetine works for anxiety, or metoprolol works to lower blood pressure. Agonism induces some kind of change or activity in the target. So we can say that it can produce theoretically up to 100% specificity, 100% efficacy. Efficacy is commonly just abbreviated as an E. Okay. Now that we have these two basics here, I'm going to introduce you to a third one that's also very important. It's called partial agonism. Now, what this means is that even if you were to occupy 100% of receptors with an agent that's a partial agonist, you can never reach 100% efficacy. So it would be, let's say this is antagonism, and this is agonism. A partial agonist may try to focus here, may lean a little bit more towards agonism, but you won't get the full effect. This can be useful in multiple drugs. An example I'll use is Aripiprazole. Aripiprazole is an atypical antipsychotic that's a partial agonist at D2. That's dopamine at the D2 receptors. There's 5 types. D2 is a primary target of most antipsychotics. Now, full antagonism of D2 has many negative effects, extrapyramidal side effects, pseudo-Parkinsonism, the list goes on, tardive dyskinesia over long periods of time. So by doing this, by using a partial agonist, you can reduce the amount of side effects because you're not fully occupying the receptors at such a level as you would with a drug like haloperidol, which is notorious for creating a dopamine blockade. Now, the final type that's important here, this is based on what's called a two-state model of receptor pharmacology. It's simplistic. It doesn't take into account different mutations and conformations of receptors and the way they can act. So, this is called inverse agonism. And I think the best way to show this to you is to create a chart. Now on the y-axis here, this is going to be y equals efficacy. Remember, efficacy is the effect on the receptor, how much of an effect it is. Now, these numbers are arbitrary, but I'm going to do 10, 20, 30, minus 10, minus 20, minus 30. We will get into deeper work later on in later lectures, actually looking at the curves, how they can shift, all the different formula you use. But this is a good introduction. This is how I learned. This is typically the way it's taught. I like it. So let's say this is 0 here. Now an antagonist, remember, 0 efficacy. So this would be an antagonist. I just made it a wavy line for visibility. Now, an agonist is going to induce a biological change. Like that. An inverse agonist can be thought of as creating negative efficacy. Now, in the presence, when you start mixing drugs together, also that applies to endogenous chemicals, you're going to get shifts, right shifts, left shifts. You're going to get changes in how all of these react together. But that is for a later lecture. Let's move on to the final. Not final, there's actually plenty of types of target interactions. But we're going to talk about ion channels here. I'm going to use Gaba as an example since my main topic of interest, and I'm quite familiar with it. So, Gaba, a Gaba receptor, it's actually an ion channel, a chloride, is composed of 5 different isoforms. There's 19 different isoforms of GABA. A little protein, we'll put some protein squiggles in here. This is what it would look like looking down straight above. There's actual images you can look up, X-ray crystallography, stuff like that. This would be the extracellular domain on top, and beneath that is the transmembrane region. So this actually creates a chloride channel. Now, what I'm introducing here is called a positive allosteric modulator. A positive allosteric modulator does not directly, the drug does not directly couple to a receptor. This is not a receptor in this term. This is an ion channel. So, the natural ligands, which would attach to the orthosteric binding site, which is the normal endogenous one, would be, let's say here, GABA. That's gamma-aminobutyric acid, is the primary inhibitory neurochemical. Primary excitatory one would be glutamate. Now this has a specific binding site, GABA. Nothing else binds directly to the GABA site. Let's take, now as an introduction, any benzodiazepine. Benzodiazepines are a class of sedative hypnotic drugs. They're also anticonvulsants and muscle relaxants. They generally affect multiple isoforms of the 19, and how specific they focus on one can cause more hypnotic effects, more anxiolytic effects, but that goes back to a receptor bias pharmacology, which is a bit more complicated. We'll get there in later lectures. So let's say we take a common benzodiazepine, one of the most commonly used, Lorazepam. Now, Lorazepam, this is Lorazepam, whatever, binds to a different site, an allosteric binding site. Now, what makes it a positive modulator? GABA will naturally open and close this chloride channel to maintain homeostasis in the brain, the balance between excitatory and inhibitory chemicals. Same thing happens with glutamate. Now, when we add a benzodiazepine, it binds in the presence of GABA. It only works in the presence of GABA. It will increase the frequency of opening and closing of the chloride channel. By doing that, you're creating a more inhibitory effect in the brain. So this is the cause for its hypnotic effect to help people sleep, can help with anxiolysis, that's anti-anxiety properties, muscle relaxant properties as well, because it is not just neurological. GABA is systemic throughout the peripheral nervous system as well. There are also negative allosteric modulators. Currently none are in use, but has a similar concept. It would shorten the opening and close, limit the opening and closing frequency of the ion channel. Now, I know this was a little bit complicated stuff here, and I jumped around a bit, but this is truly a difficult, this is the more difficult part of learning pharmacology. But pharmacodynamics is without doubt one of the basic parts. The other is pharmacokinetics, which we will deal with next in another lecture that deals with metabolism, active metabolites, how fast the body will get rid of it, how the body gets rid of it, how long it'll last in the body, the half-lives, etc. I think we've covered what we needed to cover today. Please share comments on my Twitter at at Phunky Pharmacology. Remember, these are my first 2 lectures. Tell me what you want to learn about. Tell me how technical you want me to be. And thank you for watching Phunky Pharmacology. Subscribe to be alerted to new videos as they come out. Thank you very much.